All right, let's take a look at them. So geometric series, usually kind of straightforward in that we often know automatically whether or not it converges or diverges based on just what the ratio R is. And most of these, except for the last one here, the ratio is immediately clear. Here, my ratio is 3/5, because that's what's being raised to the nth power. And since my ratio is between -1 and 1, or as I like to say, the absolute value of the ratio is less than 1, that means we get convergence. And this series converges to, or it's equal to, the first term, which would be what? Well, if I plug in n equals 1, I get 3/5. So it's the first term divided by 1 minus the ratio. Should we simplify this? Maybe. I don't know, 3/5 over 2/5 is 3/2. I don't think that's the important part, but you certainly could simplify this to 3/2. Not super necessary though, in my opinion. Let's look at, and as always, just remind, stop me if you have questions. If there's something you want me to explain more, let me know.
Where do you get the 1 minus 2?
So the general formula for the convergence or divergence, or I should say for a convergent geometric series, is that it's always going to be the first term of the series divided by 1 minus whatever the ratio is. And the ratio is just what you're multiplying by each time. So if you actually started writing this out, this series would look like 3/5 plus 3/5 squared plus 3/5 cubed, et cetera, et cetera, et cetera. And so we can see that the ratio is 3/5 because every next term is 3/5 times the previous term. For the second one, well, this one's going to be divergent because our ratio here is 7/6, and the opposite value of 7/6 is definitely larger than 1. So we get divergence. If you really wanted to, you could say it diverges to infinity because you are adding up an infinite number of positive things to get larger and larger, but I don't usually think you need to say that. All right, let's look at the next one. So for the next one, the ratio here is -5/8. That's what's being raised to the nth power, and that definitely in absolute value is less than 1. It's just easier to write that way. Like you could write it between -1 and 1, but it's just easier to slap some absolute value and say it's less than 1. And so this is going to converge as well. Okay, we have to be a little more careful what this converges to. This is going to end up converging to, again, I'm going to write it just so you can all see. It's always just the first term over 1 minus the ratio if it converges. Here our first term, well, I'm starting at n equals 2. So my first term is 4 times -5/8 squared. And then 1 minus my ratio is 1 minus -5/8. And yeah, you could simplify that. Do you really need to? Maybe if your instructor wants you to. I would say this simplifies as 4 times 25 over 64 over 1 plus 5/8, which is 13/8. And there's more you could do there, but I think you all can do that. This last one was meant to be kind of tricky, although I feel like I kind of failed at making it tricky. If you look at it right off the bat, you might think it's divergent because you kind of might think you have like 3 to the n over 2 to the n, just the opposite end. But we actually don't have that. Here, I was going to try and see if this was convergent or divergent. I might write out terms, or I might rewrite this. I might rewrite this as the sum from n equals 1 to infinity of 5 times 3 times 3 to the n. Get rid of the n plus 1 there. 3 times 3 to the n is 3 to the n plus 1. And the bottom as 2 squared to the n. If I do one more rewrite, I can think of this as the sum from n equals 1 to infinity of 15 times 3 to the n over 4 to the n is 3/4 to the n. And then I can see more easily that it's going to be convergent because my ratio is 3/4. So my ratio is 3/4. That's definitely less than 1 in absolute value. So we get convergence. And it's converged to the first term, which is 15 times 3/4 to the first over 1 minus my ratio, which is 3/4. And that's going to end up being, I think, 45. Again, not that it particularly matters. It matters a little. I feel like that's not the most important part of it. Right, this is 15 times 3/4 over 1/4, and the fourths just cancel. You should get 15 times 3, which is 45. So So geometric series, usually not too terrible to identify, and fairly relatively straightforward to see if they converge or diverge. It can be a little tricky if your things being raised to the nth power are not just straight n, like n plus 1 or 2n or 3n, but if you can rewrite it, do it that way. If you don't like this rewriting thing, another way to kind of see what the ratio is, just to kind of go along with it for a second, is we could have said, well, this series, if I really, really, really don't like rewriting it, I can just start writing out some terms. The first term, and I'm not going to do any simplifying. I'm just going to say it's 5 times 3 squared over 2 squared. And then the next term is going to be 5 times 3 cubed over 2 to the 4th. And the next term is going to be 5 times 3 to the 4th over 2 to the 6th. And at that stage, I think I can see, oh, every time I'm multiplying by 3 on top and 2 squared on the bottom. Same thing here. I'm multiplying by a 3 on the top and a 2 squared on the bottom. And that makes it, I think, fairly obvious that my ratio is 3 over 2 squared, which is 3/4. So that's another way to see the ratio if simplifying or rewriting the summation notation is not your favorite thing to do. All right, let's take a look at something that is not geometric. Let's take a look at probably my favorite example of a convergent series that is not geometric. This is kind of my go-to series if I'm looking for something that's convergent, that is not geometric. The sum from n equals 1 to infinity of 1 over n squared. We're going to show it's convergent, but we're going to talk about why it converges. So just writing out some terms, I've got 1 plus 1/4 plus 1/9 plus 1/16, and so on and so on. I do want to point out that you can look at these terms to see that this is definitely not geometric, right? 1 times 1/4 gives you 1/4, and 1/4 times 1/4 doesn't give you 1/9. So you're not multiplying by the same ratio every time to get the next term. So definitely not geometric. Also, the nth term test wouldn't tell us anything. The nth term test, not helpful. So what we're going to do for a second is just look at a partial sum, a relatively large one. Let's think about estimating the 100th partial sum, which is going to be 1 plus 1/4 plus 1/9, all the way to 1 over 100 squared. The way we're going to do this is by using some intervals. So we're going to draw a picture first. So here's the idea with what eventually is leading up to the integral test. We're going to say, well, I can draw 2 pictures. This first one, and you might just want to hold, you're obviously welcome to draw this, right? You might want to wait for just a second just to kind of see what's happening. But again, I won't actually tell you what to do. So here's the function 1 over n squared, 1 over x squared. And when I write this the first time, I'm going to write it so my rectangles are kind of bigger than the function. So there's 1, 2, 3, all the way out to, say, I don't want to go, yeah, sure, fine, I'll go to n plus 1. So my rectangles, this first rectangle, I know my function, bless you, doesn't look perfect. But the idea here is that this first rectangle has a height of 1 over 1 squared. So the area here is just the first term of my sequence that I'm adding up to get my series, right? There's my A1. And then the next one, if I use this left endpoint to get the rectangle here, there's my A2, right? The base of the rectangle is 1, the height of that rectangle is 1 over 2 squared, which is 1/4. And then so on. This rectangle is going to have an area of A3, all the way to this very last rectangle here, which is going to have an area of A sub n. Because again, the base is 1 and the height is 1 over n squared. So this area of the rectangles, so these rectangles add up to A1 plus A2 plus all the way to AN, which is SN. The nth partial sum. And what I want you to see specifically here is that the area of the rectangles is more than the area under the curve. So here we have for sure that SN is bigger than the integral from 1 to n plus 1. of our function. Right? I mean, seems reasonable. Okay, now we're going to draw another picture that gets us something similar but slightly different. So we're going to draw the same thing. Similar looking picture, but now we're going to draw the under rectangles. And all the way up to n. So my first under rectangle here, if again my function is 1 over x squared. This under rectangle has an area that's a2. The base is 1, the height is 1 over 2 squared. This next under rectangle has an area of a3, all the way out to the last rectangle here, having an area of a sub n. So this is not quite all of Sn though, right? I'm missing the first term a1, so I'm just going to add it on. So I'm going to say here is that a1 plus all these terms, which is equal to Sn, is going to be less than, well, all those terms are less than the area under the curve from 1 to n. But then I have to add on the a1 so the inequality still holds. Okay, so here's the result, or the thing that I think is really important to focus on. We can say that the nth partial sum, Sn, is bigger than the integral from 1 to n plus 1 of f of x dx, and is smaller than a1 plus the integral from 1 to n of f of x dx. And here's what's going to happen. What we're going to say is, well, if this integral converges, then certainly the sequence of partial sums is going to also converge because it's going to be less than that, whatever that integral converges to. On the other hand, if this integral diverges, then the sequence of partial sums is going to be greater than whatever that integral diverges to. Basically, the sequence of partial sums is between these two integrals. So if we know the integral converges, the whole thing converges. We know the integral diverges. Kind of neat. I think it's really neat, actually. Like it's really cool. So then what we can say basically, if we want to go back to the actual question we were asking, what we can say is that our estimate of S100 here, not that it's really the important part, but we can say that S100 is going to be less than A1 plus the integral from 1 to 100 of 1 over x squared, and is going to be bigger than the integral from 1 to 101, 1 over x squared. And I guess I should plug in the a1 is equal to 1. And then I guess we could actually do the integral. So integrating this, we get negative 1 over x from 1 to 101. Here we get 1 plus, again, negative 1 over x from 1 to 100. And so here we have, let's see, negative 1 over 101 minus 1, less than the 100th partial sum, less than 1. Plus negative 1 over 100 plus 1. So here we end up getting 99 over 100. And here we end up getting 1 plus 1 is 2, minus 1 over 100 is 199 over 100. Oh, sorry, I made a small mistake. It's not that big a mistake, but it's a small mistake. My upper limit here was 101, not 100. Sorry, that should have been 101. And so negative 1 over 101 plus 1 should actually be 100 over 101. Sorry about that. So what we're saying here is that our 100th partial sum is somewhere between 100 over 101 and 199 over 100. It's not a very tight range. Essentially, we're between 1 and 2. But what we're saying is we can then kind of see what's going to happen as we go on and on and on. So the idea here basically is that since this integral from 1 to infinity of 1 over x squared is convergent, we learned about in 21b, then so is the sum from n equals 1 to infinity of 1 over n squared. Important point. We know what the integral converges to. In fact, just as a reminder, I'll show you how we would show this integral converges, the integral from 1 to infinity of 1 over x squared. So let's use like a limit and say it's the limit as b goes to infinity of the integral from 1 to b. I would write that as x to the negative second. Then we integrate. You get the limit as b goes to infinity of negative x to the negative 1, 1 to b, which is going to be the limit as b goes to infinity of negative 1 over b minus negative 1 over 1. And then as b goes to infinity, that's going to go to 0. So we just get 1. So this integral converges to 1, which means the series converges. But we don't know what the series converges to. So I will say it is actually known what this series converges to, but generally, if you're using the integral test, it's not going to tell you the value the series converges to if it converges. We don't know what it converges to. Or at least we generally would have to do a lot of work to find it. This series does converge, I think, to pi squared over 6. Not that you need to know that at all, but it is just an interesting piece of information. Question so far? Okay, so let's write down the integral test, because the integral test is useful, although I would say it's kind of a method of last resort, even though we're talking about it first. So yeah, I would certainly try, once you've learned most of the tests for seeing if a series converges or diverges, I would say the integral test is kind of like the last thing you want to try usually, but it's useful to give us some other things. So the integral test says the following: for a positive continuous decreasing function where x is greater than whatever number we're kind of starting at, if your sequence a sub n is equal to your function evaluated at n. So basically, your function might be 1 over x squared. Your sequence is 1 over n squared, or whatever we're calling it. Then the following is true: if the integral from n to infinity of f of x converges, then so does the series from n equals n to infinity a sub n. And similarly, if the integral diverges, then so does the series. It's actually a stronger statement than that. You can actually say it's an if and only if statement. If the series, whatever the integral does, the series does, and vice versa. So if you know one of them converges or diverges, you know the other one converges or diverges, and vice versa. You know the series converges or diverges, you know the integral does the same thing. The short way of saying this is just the integral and the series have the same behavior. One of them is convergent, so is the other one. One of them is divergent, so is the other one. So this is useful if you have a series that looks kind of terrible, like the series from n equals 3 to infinity of the natural log of n over n. I will point out there's certainly an easier way to show that the series does what it does, but we don't have that test just yet. So let's talk about how we do it using the integral test. Well, we have to check a few things. Really, we should exhaust, it just got really bright in here. We should exhaust our other options. Nth term test, and we should always check the nth term test. It's not going to work out though, right? The limit as n goes to infinity of natural log of n over n. If you use L'Hopital's rule one time, you're definitely going to get 0. No help. Definitely not geometric. So, and it's probably not telescoping either. So I can integrate this though. The integral from 3 to infinity of natural log of x over x. Oh, I should have checked the things though. Is that function positive? Well, at least positive on the interval I'm talking about. Yeah, it is. Natural log of 3 is just slightly positive, and then every larger term is positive. And it's certainly positive. It's definitely continuous on the interval. Not continuous at 0, but 0 is not an interval, so we're fine. And the hardest one to always check, and fortunately you kind of supposed to check it, is it decreasing? We probably should check the decreasing. So the difficult way to check this function decreasing is to show that, like, if you plug in bigger values of x, it gets smaller. The much more typical way to show a function is decreasing is to show that its derivative is negative. So to show that this is decreasing, we would take the derivative of the natural log of x over x. And we would get the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And that simplifies to 1 minus the natural log of x all over x squared. And that's certainly going to be negative if x is larger than e. If x is larger than e, the natural log of e is 1, and 1 minus something larger than 1 will be negative. Well, that's great because in our interval, x is larger than e, so we're safe. This function is always decreasing. Checking decreasing is something we do have to do for other things as well later on, so it's a skill we should probably work on. But yeah, one easy way is typically just taking the derivative and seeing that it's negative. All right, so I want to see what this does. I always am at kind of a crossroads here. How precise do we need to be? Some professors are really kind of big on everyone using like the limits and everything. Some people are kind of more cool with you just saying, well, I know how to do this. I'm going to be a little hand wavy. I'm going to be precise this time, and I'll talk about how you can be less precise in the future. I should really write this as the limit as b goes to infinity of the integral from 3 to b of the natural log of x over x. Well, how do I said I can integrate this. How do we integrate the natural log of x over x? I think it's a u sub, right? If we let u equal the natural log of x, du is 1 over x dx. So we're doing the integral of u du, which is just u squared over 2. So we're going to get the natural, I should write the limit. The limit as b goes to infinity of the natural log of x squared from 3 to b. And then we plug in our b and our 3. The limit is b goes to infinity of the natural log of b squared minus the natural log of 3 squared. And as b goes to infinity, what happens to the natural log? I always have to think about the graph. I think about the graph of the natural log. It's getting bigger and bigger and bigger, right? It takes a really long time to get larger and larger and larger, but it does get infinitely large. This natural log of b does go to infinity as b goes to infinity. So this limit is infinite, which means our series diverges. Questions about any of this?
Go over like the use of real quick.
Yeah, I made not one. Well, I made a tiny error here. I forgot to divide by 2. Doesn't really change anything. I was just noticing that. So the u sub, when I saw the integral of natural log of x over x, I knew to let u equal natural log of x because its derivative is also in there. So the derivative of natural log of x is 1 over x. So when I was doing this, right, when I was doing the integral of the natural log of x over x, like, oh yeah, u equal to natural log of x seems reasonable because the derivative is 1 over x times dx. So I'm really kind of thinking about rewriting this as the integral of natural log of x times 1 over x dx. And then that's my u, and that's my du. And then we just rewrite it as the integral of u du, and then we use the reverse power rule, and get u squared over 2, which is the natural log of x squared over 2, which I forgot the over 2. All right, it looks a little messy. I should do that. That was better. Let's look at another example. Again, I will point out integral test, not my favorite test to use. Usually there's better, easier things to do, but it is super useful for a couple things. But let's do one more kind of neat example. and then we'll talk about the other thing we really use it for. So let's say we want to do the series, the sum from n equals 1 to infinity of e to the n for 1 plus e to the 2n. Okay. I would have no idea how to do, well, that's not true. We could probably come up with something else once we learn things. But currently, I don't see any good way to do this. Certainly, right, the nth term test doesn't work. There's no help. It's not geometric. You don't have just one thing raised to the nth power. And the reason I'm saying these things is because these are things we should check first. I should use the nth term test, but if I do, the limit's going to be 0. I should see if it's geometric. It's not. So then I start thinking, well, the only other thing I've got right now is the integral test. So I'm going to look at, well, first I'm going to look at saying, can I do the integral of e to the x for 1 plus e to the 2x from 1 to infinity? And importantly, is this function, is my function f of x positive, continuous, and decreasing? The first two are usually really, really easy to check. It's for sure positive. E to the x over 1 plus e to the 2x, always positive for any value of x. So positive, check. Continuous, yeah, it's continuous as well. E to the whatever is a continuous function, and the quotient of it, unless you had division by 0, which you don't, definitely continuous. Decreasing, that's the one that we probably have to actually check. So I'm going to do the same thing I did before. I'm going to take the derivative of f of x equal to e to the x over 1 plus e to the 2x. All right, so my derivative here is a little messy. The bottom times the derivative of the top minus the top times the derivative of the bottom, which is 2e to the 2x, all over the denominator squared. The nice thing about using this to check if something is decreasing, if you're trying to see if this is negative, denominator doesn't matter. The denominator always being squared is always going to be positive, and it's always going to end up being positive if you're using the quotient square if you're using the quotient rule. So really, we're just worried about the top here. So this is, let's see, e to the x plus e to the 2x times e to the x is e to the 3x minus 2e to the 3x all over, I don't really care. And then simplifying the top a little bit more, I've got e to the x minus e to the 3x over whatever squared. And that's e to the x times 1 minus e to the 2x over whatever squared. So when does it start being negative? Well, if x is 0, e to the 0 is 1, and 1 minus 1 is 0. And then as soon as you get a little bit bigger than 0, like when x is 1, e to the 2 is 8. 1 minus 8 is definitely negative. So this is certainly negative if x is greater than or equal to 1. So we're good to go. People get pretty hand-wavy with this. Most of the time, people don't check this stuff. And they're like, yeah, it works. It's fine. And just do the thing. But technically, we're supposed to check that we meet all the requirements of the test before we use the test. So now to integrate this. Again, I see a potential U substitution. And typically, not that there's a lot of integrating in 21C, but there's some. If I'm trying to do an integral, U sub is the first thing I'm going to check to see if I can use. What's a good candidate for U here? Well, I'm always trying to pick a U whose derivative is also in there. And so even though it might not seem super straightforward, I'm going to pick U equal to e to the x. Because my derivative of e to the x is e to the x times dx. And I for sure have an e to the x times dx. So I've got the integral of e to the x dx over 1 plus, it might have been helpful if I had thought of this instead of as e to the 2x, it's e to the x squared. Because then I can see, great, there's my du, and there's my 1 plus u squared. So I'm really doing the integral of 1 over 1 plus u squared. It's everyone's favorite function to integrate because it's the arc tangent of u, which is going to be the arc tangent e to the x. So when I'm doing these integrals that have lots of kind of stuff in them, I really like to do just the straight antiderivative on the side and then go back over here and plug in all the machinery. All right, I'm going to do this in kind of a hand wavy-ish sort of way, just to kind of show you how you might be able to do a little bit less work. Instead of using a limit, I say I'm going to do it. It feels really wrong to even think about doing it this way. But it's fine. It's okay. So I would say this is going to be, oh, I don't love it. I really, okay, fine. I can do it. I can do it. The integral of this is the arc tangent of e to the x from 1 to infinity. I really feel like I should be writing a limit here, but I'm not. It's fine. So what we're essentially getting is the arc tangent of e to the infinity minus the arc tangent of 1. Now, what happens to the arc tangent function as the input gets infinitely large? This is something that comes up more often than you would think. This goes to pi over 2. And the arc tangent of 1 is pi over 4. So this actually converges to pi over 2 minus pi over 4, which is pi over 4. Which means this integral, sorry, this series is convergent. Now, I can certainly talk about this more if any, like I should just mention. So just in case you're unaware of why arc tangent is doing this, right? The arc tangent function looks like this. It's just tangent, the middle part of tangent flipped around the line y equals x. So here's the arc tangent that has horizontal asymptotes at negative pi over 2 to the left and positive pi over 2 to the right. It looks kind of like this. So if you're thinking about arc tangent, if you think about the input getting infinitely large, the output's getting closer and closer to pi over 2. Kind of neat, kind of weird. Okay, so why do we really care about the integral test? I mean, not that it's not useful, and certainly if you've run out of other options, it is a good thing to remember that we can do. Sometimes, especially something like this, there might be other ways of doing this, but this is probably the most obvious way to. But really the reason we like the integral test a lot is because it gives us the p-series test. So here is the p-series test. It's not really a test, excuse me, so much as just an observation, but we can throw in the word test if we really like to. The series from n equals 1 to infinity of 1 over n to some power p converges if p is strictly greater than 1, diverges. Some people like to say if p is between 0 and 1, you don't really need to include the 0 part, although you can. I like to say just if p is less than or equal to 1. Because if p is negative, this certainly diverges. I just want to point out, I think it's fairly clear. Clearly, the sum from n equals 1 to infinity of 1 over n to the negative third is divergent, because this is just the sum from n equals 1 to infinity of n cubed, and that is divergent because it fails the nth term test, or the test for divergence. You could also say that it diverges because it's a p-series where p is less than or equal to 1. Either statement is true, although, yeah. So yeah, some people like to include a bigger than or equal to 0 there because they like to, but I don't think you need to. So this is totally true because of the integral test, right? We can see that the sum from n equals 1 to infinity of 1 over n cubed converges because the integral from 1 to infinity of 1 over x cubed converges. And in a similar manner, the sum from n equals 1 to infinity of 1 over, say, the square root of n diverges because the integral from 1 to infinity of 1 over the square root of x diverges. But we don't want to have to refer back to the integral test every time we have something so straightforward as a p-series. So we're just going to say, well, as long as that power is larger than 1, we know we're going to get convergence. As long as that power is less than or equal to 1, we know we're going to get divergence. So the sum from n equals 1 to infinity of 1 over n to the 5th definitely converges because our p is larger than 1. the sum from n equals 1 to infinity of 1 over, I like n, definitely diverges because p is less than or equal to 1. I should point out here p is equal to 5, here p is equal to 1. Oh, I know what I want to say. So technically, when we're talking about p series, it's supposed to start at n equals 1, and it's supposed to be 1 over n to the p. But really, you could start at any later value of n, and you could slap on any kind of constant above that if you wanted to. So I should say more generally, you can really say the following. The sum from n equals any number n, where n is greater than 1, greater than or equal to 1, to infinity of any constant over n to the p, converges and diverges for the same values of p. This certainly converges if p is strictly greater than 1, diverges if p is less than or equal to 1. And this kind of brings up what I think of as a common theme, which is that when you're talking about convergence or divergence, it doesn't matter if you chop off the first however many terms. If the whole thing converged already, it added up to something finite. And if you take away a finite number of terms, it's still going to be finite. On the other end, if the whole thing diverged, something like infinity, and you chop off some finite amount of terms, the rest of it is still going to be infinitely large, because infinity minus something finite is still infinite. So you can start anywhere you want, and it doesn't change the behavior. Similarly, you can multiply by any non-zero constant, I should say c is not 0, and not change the behavior. If some of things diverged, then multiplying them all by 5 still makes it diverge. If some sum of things converge, multiplying them all by 5 still makes it converge. It just converges to 5 times whatever you had before. I feel like this comes up a lot, so it felt worth saying. How much time we got? Not a ton. Who's the person who's, no, I was just gonna ask, are any of you in the class that meets at this time? Obviously not, because you're here. Well, I mean, that's not true. You could be in the class that meets at this time, but I would encourage you to go to class. I feel like in that class, I saw some people with some interesting, some interesting error estimation problems. So let's look at one more thing about this integral test, and then we'll move on to the comparison test. So let me say the following. Suppose that the first 4 terms of the sum of 1 over n squared from n equals 1 to infinity, which would be 1 plus 1/4 plus 1/9 plus 1/16, which is equal to 205 over 144. I should not say equal to, really. Suppose the first 4 terms of this are used, here they are, to approximate the entire sum. How good is our estimate? Or in other words, what's the error? Well, we can bound the error. The error, which would be written as the following way. So the error here, if I'm using the first 4 terms, and I think I should write this out because it's, So if we write this here, sum from n equals 1 to infinity of 1 over n squared, and it's a1 plus a2 plus a3 plus a4 plus a5 plus a6 forever and ever and ever. If these terms are estimate, which is our 4th partial sum, then these remaining terms are the exact amount of error, which people typically call R4. The remainder after the first 4 terms. That's our exact error. And we're going to estimate this the same way we were estimating the partial sums before, by just using the integrals. So we can say that, I'm always not so great at drawing pictures here. But basically, the idea here is that if you start somewhere at n, and we use the upper rectangles, then this a sub n plus a sub n plus 1 plus a sub n plus 2 forever and ever and ever is certainly going to be larger than the integral from n to infinity of your function. And in a similar way, always running out of room at the wrong moment. If we start at n also, we use the lower rectangles. So here we've got this area is a sub n plus 1. So a sub n plus 1 plus a sub n plus 2, and so on and so on and so on, is going to be less than the integral from n to infinity of f of x dx. So what we can say is that our remainder, a sub n plus 1 plus a sub n plus 2 plus all the way forever and ever and ever, is less than that. And bigger than the other thing. So that's how we can bound. Oh, sorry. If you can't see something, let me know. Sometimes I start writing off then the paper. I'm like, oh no. So this is our remainder after adding up the first n terms. And these are the bounds on the remainder. So in this particular example, if we're looking at R4, we can say that R4 is going to be between the integral. I feel like I lost an m. Sorry, there's an m plus 1 there that I lost. The integral from 5 to infinity of 1 over x squared, and the integral from 4 to infinity of 1 over x squared. So that's one way of bounding the error if you're trying to estimate what the series actually adds up to. And you can calculate both of these. They're not too terrible. This is just going to be, I'm going to do it again, even though I don't love doing it. It's going to be negative 1 over x from 5 to infinity. Negative 1 over infinity minus negative 1 over 5, which just ends up being 1/5. And here we get the same sort of deal. Negative 1 over x from 4 to infinity, which ends up being just positive 1/4. So our estimate, S4 being 205 over 144, has an error of at most 1/4. Specifically between 1/5 and 1/4. That's, I think, moderately useful. Sometimes the reason I bring this up is because someone I saw yesterday in the class that meets during this time had a question that was they were trying to use this idea to estimate, to find out how many terms you would need to use so that your error was less than some amount. All right. Yeah, let me use the last couple minutes here to briefly introduce one example. Comparison test. So does this series from n equals 1 to infinity of 1 over n cubed plus 5 converge or diverge? Well, my 3 looks bad. Anyway, it's almost like a p-series, but it's not a p-series. So I want to stress here, we can't say it converges as a p-series. So, point of fact, not a p-series. Nth term test fails, not geometric. So, oh, and also the integral test. The integral test also, I don't know how to integrate. Maybe we can't. Can we integrate 1 over x cubed plus 5? Maybe. It's probably terrible and requires partial fractions. So not that you couldn't use the integral test, potentially, but again, last resort method. Only use it if you've run out of other things to do. Here, we can say, well, even though I don't know what this is, I know it's less than something. It is certainly true that 1 over n cubed plus 5 is less than 1 over n cubed for every positive n. right? Bigger denominator means a smaller fraction. So that means that this series is certainly less than this series. But this series is convergent, which means this series also has to be convergent. Again, there's a few things we would probably need about how the function is non-negative, and well, no, that's it really, it just has to be non-negative. So this series converges by direct comparison.